So I don't have too much to say. We're going to start with the talk from Fabien, which is recorded. Play that. I'm going to let someone will chair the first session, and I will chair the later session tonight. Hopefully, you'll be able to watch and attend all the sessions. We're running so how many talks do we have in the first session? So someone just remind me. It's
6 talks in first session and 5
okay,
in
6. Okay, and then 5. Okay, and then there's a break between the 2 sessions.
Yeah, 45 minutes break.
All right. Okay, so my hand over to you. Thank you very much to everyone. And I'll see you guys. Hopefully you'll be able to stay to the end. All right, thank you.
Thank you. Let me share screen.
In WaveWatch, mainly for operational purpose. Now Emilio has moved to Australia, is in CSIRO, and I've also worked on that with Martin and Carlo. And basically, what we really wanted to do is look at all the different ways that WaveWatch has parameterized ice-induced wave damping, and see if some of these parameterizations emerge as performing better than others. So if you're not familiar, although I'm pretty sure most of you are, but so WaveWatch is what we call a spectral wave model or a phase average model. And
is it audible to all, this recording? Can anyone confirm me?
We lost.
And the way this model works is that they describe
it's not audible?
the principles of this function here, the wave action density. I'm going to define in a second. On the
I can hear it, Susan, but I can't see it.
Okay, just a moment.
on the surface, and basically what we really wanted to do is look at all the different ways that WaveWatch has parameterized ice-induced wave damping, and see if some of these parameterizations emerge as performing better than others. So if you're not familiar, although I'm pretty sure most of you are, but so WaveWatch is what we call a spectral wave model or a phase average model. And the way this model works is that they describe the transport of this function here, the wave action density, I'm going to define in a second, on the surface of the oceans on global scale. And so it satisfies here the transport equation, as you see here. CG represents the group velocity. So that's the speed at which waves travel, essentially. And then on the right-hand side here, you have S, which is the source function, right? So if it's 0, then it's just a transport which preserves the spectrum. And if it's not 0, then you have other things happening. So this wave action density, so it is a function, of course, of space and time, but also of frequency and direction. And you can think of it as a measure of wave energy. But the phase of the waves, of course, is not resolved. That's why it's a phase average model. And the source function here, it is an attempt at representing the effect of various forcings and inhomogeneities on the transport of the wave spectrum, right? And there are many different source terms which make up S here in WaveWatch, although you don't have to use them all the times, but here are a few of them. So of course, there is a forcing from the wind. SDS represents the dissipation due to white capping, some nonlinear interactions, some effect of bottom of the seafloor, especially near the coast. And of course, there is one for the ice as well. and there's others. And so WaveWatch 3, I should say, is, I think, arguably the most widely used spectral wave models. There are others, but I think WaveWatch 3 is the one that is used the most. And one of the reasons that I think it's been used quite a lot, especially in our circles here, is because there has been a lot of work put in on trying to parameterize the damping of waves caused by the ice. And that can be caused through various physical processes, such as turbulent dissipation in the fluid, some viscous ice rheology, also wave scattering, and other things. And so this source term here as ice, the standard and simplest way it is parameterized is in this functional form here. And so you have basically these four terms. So C here represents the ice concentration. So as you can see, it linearly depends on ice concentration. So the more ice you have, the more damping you have. That's essentially what it says here. But it says it should be linear. And alpha here, so that's this key parameter, which we call the attenuation coefficients. And that describes essentially the rate at which waves attenuate. And so WaveWatch currently has 14 different ways of choosing alpha, the attenuation coefficient. So, you know, if you put yourself in the position of using WaveWatch for the first time, that can be overwhelming. Where do you start? Which one do you choose? And so that's essentially, you know, part of what we wanted to address here. So let me just give you a brief breakdown of all these different parameterizations that exist here. The first one, and this basically will so these will be listed in more or less chronological order in the way they came into the model. So the first one that was there is basically was to treat sea ice as land, approximately. There's kind of a buffer region depending on ice concentration, but basically it should be ice as land. And that was in the first release of WaveWatch, where they didn't really want to deal with the ice. And then some different parameterizations were released over time. So IC1 is the first one where alpha, the attenuation coefficient, is a constant. So it's just a number you put in. Then IC2 came in, and there's several versions of it, but in the latest version, it basically parameterizes the attenuation coefficients through some eddy viscosity parameter, which depends on the flow regime, whether it's laminar or turbulent. So that's why it depends on the Reynolds number. IC3 came out as something that was supposed to represent what the ice actually looks like, and so it's basically based on a model of a viscoelastic ice layer floating at the top of the water, which depends on a range of rheological parameters such as viscosity, elastic modulus, and so on, and thickness as well. But let's say you fix all these parameters, what you end up with at the end is alpha, which is a function of frequency, and that's the first parameterization which recognizes this the importance of this frequency dependence of the attenuation coefficients, which has been observed in many different analyses. And then came out these IC4, so there are 7 of them, IC4M1 to IC4M7, and these are based on empirical. So these are empirical parameterizations, and there are 2 types. Some of them are based on model outputs, and some of them are based on direct observations. And then the last set of parameterizations, the IC5s, there are 3 of them, and they are similar to IC3. So they model the ice cover as a viscoelastic effective medium, although they are simpler than IC3. And also they give an attenuation which depends on frequency. All right. So you can count if you want, but that's 14 of them. Okay. So despite having so many different choices for choosing the ice damping in WaveWatch, there have not been that many studies that have compared their performance. And in fact, I think there are only two, as far as I know, at least. And so I'll just give you a brief breakdown here of them. So the first one was by Lee et al. In 2015, where they did a hindcast of the SIPEX2 experiments in the Southern Ocean, 2012, which may be known for the Nature paper that came out of it, led by Alison Kohut. And here they compare to the performance of 4 parameterizations, IC0, IC1, IC2, IC3. So they tune the parameters of the different models to obtain a better fit. And essentially, they looked at how it compared. So here what you see is the significant wave height over time. There are 2 wave buoys which were tracked, and you can see that the models are able to reproduce roughly some of the features that are observed here. And I think their conclusion was IC3 was the best performing one. Although arguably IC3 has more parameters, so you can tune it more easily to fit observations. And then there is this 2020 study by Liu et al., where they looked actually at 2, so they did a hindcast of 2 wave buoy deployments. So the same one as before, SIPEX2, but also the C-State 2015 wave buoy deployment in the Arctic. And here I'm just showing results here from their paper, looking this time. So that's a scatter plot of significant wave height at the top and mean wave period at the bottom here. And these were they compared the IC5 parameterizations. Here there are only 2 of them. So the middle one here, that's IC5M1, and the last one here is IC5M3. And the one here at the front here, that's an extra one they run where they remove the ice entirely, which is a nice one to have for comparison purpose. And what they found here is that, yeah, it seems like model is doing a fairly good job, although they didn't really resolve the small wave energy. But if you look at the mean wave period, there is a clear bias here where the model is clearly underestimating the mean wave period consistently. All right. And so what we did here is something very similar, but instead of just picking and choosing a few of the available parameterization, we picked all of them. So we ran hindcasts here for all 14 parameterizations of the SI source term here. And we did that for the 2017 Piper's wave deployment in the Ross Sea. And our goal was essentially to compare the performance and identify consistent biases in WaveWatch generated data. Okay, so why did we choose this Piper's deployment? And that's because there is a lot of data that came out of it. So it was in the ice growth season, April to July 2017, and 14 buoys were deployed. And there was a range of wave conditions and also of ice conditions observed. So there were calm, but also large storm events. There was of course pancake ice conditions, but also the buoys were deployed really far into the ice cover where the ice was nearly continuous in some cases. Something to say here is that wave direction was not recorded by these wave buoys, so we only look at the one-dimensional spectrum, so with respect to frequency. Okay, so we ran 15, not 14 actually, hindcasts. So the 14 hindcast for the 14 different SI parameterizations, but also we did a no ice run. So we just removed the ice and set the concentration to 0 everywhere. And again, that's a nice baseline to have here to compare our results. And so the way the hindcasts were set up here is we ran we ran a hindcast on a regional, so a nested regional run at fairly high resolutions, which was forced on its boundary by a lower resolution global run. And the concentration and thickness were actually included here and were taken from the ERA5 reanalysis. And the only thing that we looked at here were the spectra, so the wave spectra, again, one-dimensional spectra as a function of frequency only, along the buoy track. So what we want to do really is compare the spectra on either side for WaveWatch and the buoys. Okay, so this is just to give you an idea here of the deployment. So we had 4 wave buoys here on the west side, and then there were 9 more buoys here on the eastern side, which were released at 2 different time periods here, and you kind of see their tracks over time. This is just a snapshot here. I think this one was taken on 15th of June, but some of the buoys had died already by then, and some just kept going afterwards. Okay, so let's get into it. So what we obtained from this analysis was 3,898 wave spectra, which were collocated as with the ones recorded by the buoys. And we had that for all 15 hindcasts. So that's a lot of data to go through. But the first thing I thought I would do here is actually, well, what if we just average all these spectra together and see if something just interesting comes out? And that's what we have here. So here, this is just the average spectrum. So for each wave frequency, just the average over these 3,898 values. And already something interesting is happening here. So the data from the buoys is these crosses, and then you have all these different models which are all over each other here. But what we can see here already is that there's clear biases both at low frequency and high frequency. Since at low frequency, so the model seems to significantly underestimate these spectral values here, but at high frequency, it's the other way around. The model seems to overestimate spectral amplitude. So at low frequency, we potentially explain that by an issue with the wave buoys, and that's based on some earlier analysis we've done of the wave buoys, which shows mixed results at very low frequency, in particular below 20-second wave periods. So what we did is we just cut off the spectra here at this 20 seconds, so 0.05 hertz frequency, and did not consider that beyond in our analysis. But at high frequency, we had already done some filtering in some previous analysis, so we think that we trust here what's happening in the wave buoys. Now, interestingly, in the middle, it seems like there is some overlap, so that's good to see. All right. So here I'm just showing some results, so selected results for just 3 wave buoys, and 4 models, so 4 parameterizations, so IC2, IC3, IC4M2, and IC5M2, which were not chosen for a very specific reason, apart that they span a range of different types of parameterizations, and we also include a no ice run. Now, obviously, if the no ice run consistently have higher significant wave heights because, of course, there is no attenuations from the waves, and that's reassuring to see that when you include the ice, both in the model and the data, we have less energy. So indeed, the ice attenuates the waves. So that's reassuring. Now, if you look more carefully here at those patterns, it seems like the models and the data are not too far from each other. Especially if you look at buoy 1 here, we have some nice correspondence. Also in buoy 10, a little bit less in buoy 6. So the buoys here, by the way, are these green crosses, and all the models are behind. And then if you look at these different, why buoy 1 and buoy 10 are doing better than buoy 6, then all you have to do is basically look at the concentration below here. So at the start, especially here for buoy 1, concentration was pretty low. And for buoy 10, concentration was also relatively low, especially in the later stages, while for buoy 6, concentration was pretty high, remains high pretty much through the duration of the life of buoy 6. So it seems already that the performance of the models significantly depends on ice concentration. Now, if you look at the mean wave period, which is what you see in the second row here, then again we have similar results, so fairly good correspondence in low concentration, while at high concentration, that's buoy 6 here, all the model seems to significantly underestimate the mean wave periods by at least a couple of seconds. All right. So now let's combine all the buoys together and just look at these scatter plots here. So on the vertical axis, that's the model. On the horizontal axis, that's buoys. And here, the top rows of these panels here are significant wave height, and the bottom row is the mean wave period. And in color here, you can see the influence of the ice concentration. And so, again, here something consistent seems to emerge. At high concentration, we seem to have a bias that the model overestimates significant wave height consistently, while the model seems to be performing slightly better, although maybe this a little bit underestimates significant wave height at lower concentration. And for the mean wave period, yeah, again, these results are consistent across the different model parameterizations here, where especially at high concentration, the model seems to underestimate mean wave periods. So it seems like there are consistent bias here, which emerge at high ice concentration. So now if we look at the correlation coefficients, comparing all the models here together, that's the results that we get. Okay, so on the vertical axis, you have all the different models, including the no ice run, at the bottom one here. And on the horizontal axis, that's just the correlation coefficients for significant wave height and mean wave periods here on the right. And what I've also included here is a measure of bias. That's the color. Because it's interesting to see that the no ice run is highly correlated in a significant wave height to the observations. But if you look at the bias is actually the highest, and that kind of makes sense. Of course, if you remove the ice, then basically what you get is the forcing. So what this correlation means that the response and the forcings are correlated to each other, which is not surprising. So even though the no ice here has high correlation, it doesn't mean that it's a good model because it has large bias. But otherwise, clearly, we see that some models performing better than others, and some are doing very poorly, at least 4 of them here. And we have a few of them which are pretty good, both in correlation and in having lower biases. There's a bit more bias here in mean wave periods. And what we found here, and it's more or less arbitrary, but if you look at these models which have correlation coefficients higher than 0.5 in both significant wave height and mean wave periods, then there are 9 of them, and I've listed them here. So IC2, IC3, IC4, M2, and then a few more there. So these are the ones which we thought, might have a better chance of working. Then we wanted to see, well, why does this happen? And so the attenuation coefficients, which is parameterized, in each of these parameterizations, then how does that compare to those actually we can compute from from the data themselves. And so that's kind of my attempt here. So that's kind of weird plots coming, but hopefully just keep with me for a second here. So that's my attempt of representing the range of attenuation coefficients as a function of frequency of all these different models. Now, these models, of course, depend on parameters such as ice thickness. So what I wanted to do here is represent a range of values of these attenuation coefficients for different ice thickness. So that's why you have this shaded region in some cases here. And then overlaid here, you have these data points here, and these are values of the attenuation coefficients as a function of frequencies, which were extracted directly from the data, the Piper's data, and that comes from a paper we published a couple of years ago. And what's interesting to see here is that most of the models, most of the parameterizations for alpha seems to have alpha values lower than those that we measured. So when we see that the model seems to overestimate wave energy or significant wave height, then it could simply be a fact that, well, the parameterizations simply of alpha are just too low. And the parameters which describe these models need to be adjusted to increase these values. All right, just one more result here, and that's potentially a bias, a reason to explain the bias that we observed here, especially in mean wave period, is, well, maybe the dispersion relation in the ice is different to the one in open water, and therefore the wave speed that is predicted by WAVEWATCH, which for most of this parameterization is the same as in open water, is not right, and that could introduce some kind of time delay here, essentially between the model and the observations. And so the question here, what I wanted to do is have a look at is correlation somehow improved if we time shift WAVEWATCH III generated data. And if you do that for low ice concentration, which I argue is a proxy for close to the ice edge, then you can see that here the peak on the correlation coefficients in significant wave height is at a time shift of 0. So it seems like here there is no reason to think that the dispersion is wrong here. But if you look at higher concentrations, so larger than 85%, then here you can see that these curves here are clearly are not as clearly peaked here at t equals 0, and can be argued in some cases t equals 1, so that's 1 hour, that is, that there could be a peak there. So it's possible that further into the ice here, basically the WAVEWATCH III is making the wave travel too slow, right, compared to what we observed. Okay, so just here to conclude, so it seems like WAVEWATCH III performs best for larger wave events and at low ice concentration. That is consistent, and also we observe clear biases in both significant wave height and mean wave period, which depends strongly on ice concentration. So most of these SIS parameterizations, which we used with their default parameter values, they underestimate wave damping rate or attenuation coefficients, and also we found evidence that WAVEWATCH III slightly underestimate the wave speed, especially at high concentration or far from the ice edge. And so the next step, of course, here would be to look at, well, can we improve these model fits here by optimizing the parameters of these different parameterizations? One more thing that we haven't tested, but something that would be nice to look at is scaling this ice damping curve in WAVEWATCH linearly with ice concentration appropriate. And there's evidence that shows that it might not be actually based on observations. And then potentially might need to develop new parameterizations to improve the ones that are currently there, which I would argue none of them is likely to do the job consistently for all types of ice conditions and wave conditions. And that's me. Thanks.
We must thank Fabien, but unfortunately Fabien is not here. But the presentation was very nice with so many informations. But we can ask questions through email to Fabien. Fabien asked to send him email if there is any question. He has some urgency, so he is not here. Let me go to our next talk. Professor Giulio Passerati from the University of Melbourne, and he will present on what images of sea ice tell us about the marginal ice zone. Professor Passerati, now
Yeah,
you can
hi.
start.
Yeah, doctor. Yeah.